Hi, my name is Alex Mazursky from the University of Chicago, and today I'd like to talk to you about our work on a new type of haptic actuator to add tactile output to everyday objects. This work was done in collaboration with my colleagues Shan-Yuan Teng, Romain Nith, and our advisor, Pedro Lopes. What you see here on screen is our new haptic actuator, and it is currently vibrating against the user's finger pad. When we move the finger away, we can see that the vibrating element is a magnet, and it is being excited by a coil worn on the fingernail. Now, this is not unlike classical vibration devices, such as linear resonant actuators. We too incorporate the typical coil, magnet, and spring. However, what is new is that we have mechanically decoupled the active component, the coil, from the passive components, the magnet and spring. No wired tethers, electronics, or batteries are needed within the haptic patches themselves. Therefore, the benefit of this decoupling is that we need only one power source to actuate any number of passive patches in an environment. We see this as being akin to ubiquitous sensing, specifically passive approaches, but for haptic output. Let me use some applications to illustrate how MagnetIO works. Here we see a user in their home using MagnetIO to control their environment. The user wears our coil on their nail, and as they walk inside, they tap the patch on their door and are met with two vibrations, confirming in an eyes-free way that their home alarm is now disabled. Next, the user walks to a patch on their wall that controls their thermostat. As the user slides their finger to adjust the temperature, MagnetIO senses which part of the patch the user is touching using a magnetometer built into the coil. According to where they touch, they receive haptic feedback to indicate the setting that they have selected. One factor that enables placing these patches on many surfaces is that they are soft and flexible because they are made from mostly silicone. Next, the user picks up their toy, which has a heart-shaped patch on its chest. They can feel its heartbeat with MagnetIO. When the toy is shaken, the onboard IMU detects the movement, and the heart rate and vibration speed up accordingly, before slowing down again after no movement is detected. I'll now detail how we implemented this actuator, beginning with the nail-worn coil, which acts as a wearable power source. This has an IMU with magnetometer, the coil itself, a LiPo battery, microcontroller, motor driver, and Bluetooth. Our coil is designed to provide strong magnetic forces while maintaining a compact, lightweight footprint that importantly does not occlude the user's finger pad, because we believe it is important to allow the user to still feel their surroundings, in addition to the patches. The final coil design weighs just 2 grams without battery. The user only wears one of these, yet they can actuate many haptic patches, which I'll describe now. At the center of the patch is a tactile magnet, made from silicone doped with magnetic powder. This magnet is mounted on 2 thin beams of silicone that act as springs. Surrounding the magnet is a cutout, and the magnet rests within an air gap. This allows the magnet to vibrate up and down, even when the user compresses the patch with their finger. In our paper, we demonstrate that by tuning the dimensions of the spring and magnet, we can tune each patch's individual resonant frequency to elicit different tactile sensations more strongly. Finally, the patch's perimeter has 4 ID magnets that enable the patch to be uniquely detected via magnetometer. The net magnetic field of all magnets encodes a unique 3D signature to each patch. Using Bluetooth, the actuator can communicate back and forth with the main application to determine appropriate haptic renderings. Here is how we fabricate our patches, which are made of 2 parts: a soft and stretchable magnet made of silicone mixed with permanent magnetic powder adhered to a flexible silicone mechanism. First, the silicone mechanism is made by casting silicone into a mold. Next, we fabricate the soft magnets by mixing the silicone and magnetic powder. The mixture is then cast into a 3D printed mold to shape the magnet. The mold is then held between 2 strong permanent magnets, and this strong, about 1.1 Tesla field magnetizes and aligns the polarities of the individual particles. This process results in a composite with a strong permanent magnetic field, while remaining flexible due to the silicone holding it together. With the goal of maximizing magnetic field strength to produce strong vibrations, we use a magnetic powder concentration of 80% by weight. The haptic patch is then assembled by adhering the magnets to the mechanism with silicone glue. To summarize, we designed and evaluated a one-to-many actuator to allow haptic interactions to more easily scale. We tend to think of MagnetIO not necessarily as an end product, but as a hardware and fabrication idea that may inspire more ubiquitous use cases for haptics. Thank you for tuning into our talk, and please come stop by our demo and check out our paper for more details. Thank you.